Welcome to this tutorial on C++ algorithm basics. We're going to provide an overview of common algorithms available in the Standard Template Library, or STL. In this session, we will cover sorting, searching, methods for modifying sequences, binary operations, numeric operations, and much more. STL algorithms are optimized, thoroughly tested, reusable, and are compatible with all STL containers. To use algorithms in C++, you need to include the algorithm header file. This header contains around 100 algorithms designed for various operations. These algorithms work with any container that provides iterators, promoting generic programming and significantly reducing code duplication. Let's look at a basic usage example. First, include the algorithm vector and iostream headers. In the main function, create a standard vector of integers named numbers, initializing it with some values like 5, 2, 8, 1, and 9. Then, to sort this vector, use the std sort function, passing the beginning and end iterators of the vector. This will sort the numbers in ascending order. Let's delve into some sorting algorithms provided by the STL. The first one we will discuss is std sort. This is a general-purpose sorting algorithm that has a time complexity of O of n log n. It makes use of introsort, which is a hybrid sorting algorithm that uses a combination of quicksort, heap sort, and insertion sort. To use it, you simply pass in the beginning and end iterators of the container that you want to sort. Next up is std partial underscore sort. This algorithm sorts only the first n elements of a range, leaving the rest unsorted. This is particularly useful when you only need the top or bottom elements. In this example, we are sorting only the first 3 elements of the vector. The third algorithm is std stable underscore sort. This sorting algorithm preserves the relative order of equal elements in the range. This becomes very handy when you're sorting by multiple criteria and want to maintain a specific order. Imagine we have a vector of student objects, and you want to sort them by their grade while preserving their alphabetical order. std stable underscore sort is perfect for this. Finally, we have std nth underscore element. This algorithm partially sorts a range such that the nth element is in its sorted position. All elements before this nth element are less than or equal to it, and all elements after it are greater than or equal to it. It's useful for finding things like the median of a set of values. Now let's explore several searching algorithms provided by the STL. The first one we will discuss is the std find algorithm. This provides a linear search, which has a time complexity of O of n. It works by returning an iterator to the first element that matches the value you're searching for. If the element is not found, it returns an iterator to the end of the range. The next algorithm is std binary underscore search. This checks if a value exists in a sorted range and provides a time complexity of O of log n. It returns a Boolean value. Keep in mind, though, that std binary underscore search requires the range to be sorted beforehand. Then there is std lower underscore bound. This algorithm finds the first position in a sorted range where a value could be inserted without violating the sorting order. Again, this algorithm requires a sorted range to operate correctly. The time complexity is O of log n. Finally, we have std find underscore if. This searches for an element that satisfies a specified predicate, meaning it must meet a certain condition. This is extremely useful for more complex search criteria. Let's take a look at algorithms used for modifying sequences in C++. The first algorithm is std transform. This applies a function to each element in a range and stores the result in another range. For example, you can use std transform to square every number in a vector. This requires an input range, an output range, and a unary function. The next algorithm is std shuffle. This randomly reorders the elements in a range. It requires the beginning iterator, the ending iterator, and a uniform random number generator. This algorithm is useful for simulations, games, and any other application where you need to randomize data. The third algorithm is STD, replace. This replaces all occurrences of a specific value with another value within a given range. For example, we replace all instances of the number 2 with the number 9. Finally, we have STD, remove. This removes all occurrences of a specified value from a range. Note that STD, remove doesn't actually change the size of the container. Instead, it moves all the elements not equal to the specified value to the front of the range and returns an iterator to the new end of the range. Next, we will discuss numeric algorithms provided by the STL. The first algorithm is STD, accumulate. This computes the sum of a range of elements. It can also use a custom binary operation instead of addition. To use it, you need to include the numeric header. STD, accumulate, takes the beginning iterator, the end iterator, and an initial value, then returns the sum of the elements plus this initial value. The second algorithm is STD, inner underscore product. This computes the inner product of two ranges. This algorithm multiplies corresponding elements from the two ranges and sums up the results. The third algorithm is STD, partial underscore sum. This computes the partial sums of a range, where each element in the resulting range is the sum of all previous elements in the input range. Finally, we have STD, iota. This fills a range with sequentially increasing values. It takes the beginning iterator, the end iterator, and a starting value, and then fills the range with values incrementing by 1 from the initial value. Here are set operations that can be performed using C++ algorithms. The first one we will discuss is STD, set_union. This constructs a sorted range containing all elements that are present in either of the two sorted input ranges. It is similar to the union operation in set theory. We pass the algorithm the beginning and end iterators of both input ranges, as well as an iterator pointing to the start of the output range. The second algorithm is STD, set_intersection. This constructs a sorted range containing elements that are present in both sorted input ranges, similar to the intersection operation in set theory. We again pass the beginning and end iterators of both input ranges, as well as an iterator pointing to the start of the output range. The third algorithm is STD, set_difference. This constructs a sorted range containing elements that are present in the first range, but not in the second range. This represents the difference between two sets. Finally, we have STD, set_symmetric_difference. This constructs a sorted range containing elements that are present in either of the ranges, but not in both. This operation is equivalent to the symmetric difference between two sets. Let's explore the min and max algorithms available in C++. First up is STD, min_element. This algorithm finds the smallest element in a range and returns an iterator pointing to that minimum element. Next, we have STD, max_element. This is the opposite of STD, min_element. It finds the largest element in a range and returns an iterator to that maximum element. Then there is STD, min_max_element. This algorithm finds both the smallest and largest elements in a single pass. It returns a pair of iterators, where the first iterator points to the minimum element, and the second iterator points to the maximum element. Finally, there is STD, clamp. This algorithm clamps a value between a pair of boundary values. If the value is within the range defined by the boundary values, it returns the value itself. Otherwise, it returns the nearest boundary value. Now let's explore the permutation algorithms. First, we have STD, next_permutation. This transforms a range into the next lexicographically greater permutation. It returns false if no such permutation exists, meaning the range is already in its highest possible order. Next is STD, previous underscore permutation. This transforms a range into the previous lexicographically smaller permutation. Like STD, next underscore permutation, it returns false if no such permutation exists. Then we have STD, is underscore permutation. This determines if a sequence is a permutation of another sequence. If the sequences contain the same elements in a potentially different order, then the algorithm returns true. Finally, we have STD, rotate. This rotates the order of elements within a range. After rotation, the element that was initially at the middle position will become the first element. Let's wrap up with some best practices and a summary of what we've covered. When selecting algorithms, choose them based on the container type and the operations you need to perform. Always consider the time and space complexity requirements. Use standard algorithms instead of writing manual implementations to leverage optimized and tested code. Combine algorithms to accomplish more complex tasks. For performance tips, pre-allocate space with reserve when using vectors to avoid frequent reallocations. Pass large objects by constant reference in predicates to prevent unnecessary copying. Consider using parallel algorithms for large datasets to speed up processing, and minimize iterator invalidation during operations to ensure correct behavior. STL algorithms provide optimized, tested implementations that work with any container providing iterators. Take advantage of algorithm constraints like sorted ranges for binary search. Modern C++ offers parallel versions of many algorithms, and all these algorithms promote generic and reusable code. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.